Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. To close out 2018 and open the new year, we're excited to present to you our first ever AI Rewind series. In this series, I interview friends of the show for their perspectives on the key developments of 2018, as well as a look ahead at the year to come. We'll cover a few key categories this year, namely computer vision, natural language processing, deep learning, machine learning, and reinforcement learning. Of course, we realize that there are many more possible categories than these, that there's a ton of overlap between these topics, and that no single interview could hope to cover everything important in any of these areas. Nonetheless, we're pleased to present these talks and invite you to share your own perspectives by commenting on the series page at twimlai.com/rewind18. In this episode of our AI Rewind series, we're bringing back one of your favorite guests of the year, Jeremy Howard, founder and researcher at Fast.ai, to discuss trends in deep learning in 2018 and beyond. We cover many of the papers, tools, and techniques that have contributed to making deep learning more accessible than ever to so many developers and data scientists. Enjoy. All right, everyone, I am here in Montreal with Jeremy Howard, and I am speaking with Jeremy as part of a special series of shows we're doing about reflection of the machine learning and deep learning world for 2018 and some thoughts on predictions for 2019. Jeremy, welcome back to the show.
Thanks, Sam. Nice to be here. I'm worried I'm not nearly cool enough to be able to tell you much about trends and whatnot, but I'll do what I can.
I am sure we're going to have a wonderful conversation. So this is the first of these that I'm doing, and I expect that the format will shift a little bit as I do them, but maybe we can kind of start by just getting your off the top of the head kind of reflections on 2018 before we focus on some of the things in particular around deep learning research that you found most interesting.
Mm-hmm. Well, I guess it's easiest for me to talk about the year in terms of the stuff that I care about, which is increasing accessibility of deep learning for normal people to solve normal problems. So one of the, I guess our main work towards that this year has been trying to make it faster and easier and less expensive to train neural nets across more different areas. So there's a lot of people who have been doing work in that area as well, which I could touch on. So one is that when you look at the Stanford competition called Dawnbench, it kind of kicked off increased interest in an area which had been really underappreciated before, which is can you train accurate large models quickly and cheaply. So there's a competition to measure those two things. And so before the competition, it took a few days generally to train ImageNet to a reasonable accuracy, particularly if you were using kind of commodity hardware like stuff you would rent from AWS.
Right.
And by the end of it, we had gotten to first place on the leaderboard with 18 minutes, $40 using nothing but Amazon AWS. And then there's been other related work from other researchers who have got it down, not on AWS commodity equipment, but on more specialized equipment down to 7 minutes. And so the kind of stuff that's allowed that to happen has been things like fantastic work from Leslie Smith on achieving superconvergence, so using much higher learning rates, particularly an approach to learning rate scheduling called one-cycle scheduling, which we use as the default all the time now and makes life much faster and easier.
I remember in the course, and I believe our last conversation, talking about cyclical learning rates. Is one cycle
this is
an iteration beyond
this is
that?
the next stage. So last year, I guess Leslie did the CLR paper, cyclical learning rates. One cycle is just what it sounds like, which is to spend about half of your epochs gradually increasing the learning rate and about half gradually decreasing it. But there's a few really important insights you have to combine with that. One in Leslie's paper is that as you increase the learning rate, you should decrease momentum. So you have these two things happening at the same time. So if you use the Fast.ai library, that'll happen for you automatically. And so it means that as you get to those really high learning rates, because the momentum's a lot lower, you're much less likely to kind of accelerate further than the model can handle. Something not quite related to Leslie's work, but stuff from Frank Hutter's lab around being able to handle weight decay properly when you're using dynamic learning rates, so momentum and atom. So their technique's called atom W. Turns out to be super important as well for this.
Was atom W this year?
I can't quite remember if it was in the last 12 months or not. Maybe it was slightly more. I don't know. But the combination, I guess, of all these things has been very much this year. So when we combine those two together along with progressive resizing, so basically, I don't know if we were the first to do it. There was a lot of people that kind of did it all about the same time, but basically this idea of like, why don't you do most of your training on small images and then gradually resize, because modern convolutional neural nets are all, don't care what size your input is. And
what's the advantage of doing that?
Well, it's just super fast, you know. So, well, two things. It's super fast. You do most of your training at 64 by 64, so you're decreasing your compute by more than 10x. But then the nice thing is you can do the last one or two epochs at a larger size than most people. So most people do 224 by 224 the whole time. So we'll go through to 288 or even bigger.
So the intuition there being that you can teach the network the basic things that it wants to learn about edges and textures.
What does the cat look like?
Yeah.
You know, and what a cat looks like at 64 by 64 is basically the same as 288 by 288. So the last couple of epochs, it's really just learning a few little tweaks around like, okay, this breed of cat has a, this colored nose, and this breed of cat has this slightly longer hair or whatever. So it's can do most of its learning. And actually that's been a real focus for us throughout the year, is like this kind of, and same with Leslie Smith, doing a lot more stuff dynamically, changing things during training. So for example, something we're going to release next week is doing the same thing for GANs. So we've now got GANs training quickly and easily and reliably for the first time. And the trick again was basically to pre-train the critic and pre-train the generator using kind of simpler, fast approaches and on smaller images. And then at the very end, you kind of GANify it. So, that's kind of been a common theme, I think. And so a lot of that ties in then to kind of transfer learning, because all these things of like gradually increasing the image size is kind of just a type of transfer learning. It's kind of transfer learning you're doing within the training. So for our GANs, we kind of do a similar thing of this kind of transfer learning as part of the process of training again. And so in general, transfer learning lets you generalize better, lets you train faster, generally lets you use less data. So we had a particular focus, as you know, on NLP for that. And so we showed with NLP you can use like 100 times less data and still get state-of-the-art results for sentiment classification. And so that's all about transfer learning. And then Alec Radford at OpenAI, built on top of that, replacing our LSTM with a transformer. And then Google built on top of that, making some tweaks, but mainly just doing it for longer with more data. And, we're now at a point where we know, I guess we know kind of every time people try and do transfer learning anywhere, it tends to either let you get way better results on small data sets than people thought were possible, or if you use big data sets like Google did with BERT, to kind of smash the state of the art of what people thought was possible. So Still really underappreciated area, frankly. Still, most people don't know how to do it properly.
I had an interesting conversation here at NeurIPS. Someone approached me and we were just kind of exchanging thoughts on what was interesting at the conference, and they said they didn't see a lot of transfer learning.
No.
Like, did that go away? And
I haven't seen any.
Yeah. I both haven't seen it, but it's kind of being baked into a lot of things. It's kind inherent in.
But also, like, NeurIPS is very tainted by its history and culture. So the papers here tend to overrepresent either things which are very mathematically intensive or also things that follow certain trends. So at NeurIPS, every second paper is either adversarial blah or reinforcement learning blah, So it's not necessarily a conference you expect to see the most practically impactful stuff, unless some of the workshops are a little bit different. But I think that's been another feature of 2018 is like people are putting adversarial into everything and putting RL into everything, and not generally for good reasons, especially adversarial. There's this huge literature now around avoiding adversarial attacks, and I've yet to find anybody and I've asked many researchers in the field, directly, can you show me a actual practical example of where you would need to use this thing, whatever they built. And no one's managed to yet.
What about on the generative side? Are you as bearish on the GANs?
So I spent 2 weeks figuring out how to train GANs properly, and finally we now have something in Fast.ai where you can train them in an hour on a single GPU reliably. And I'm very proud that we got to that point, and we have this really flexible API that allows researchers to plug in things in ways they couldn't before. But at the same time, I was also researching how to avoid GANs, and I've figured out for generative stuff how to actually get GAN level performance without using GANs. So I'm not sure.
Is this stuff that you've written about or published somewhere?
It's coming up. So we're particularly doing some work in microscopy in collaboration with the Salk Institute at the moment.
Okay. Through Analytic or through Fast.ai?
No, I haven't had anything to do with Analytic for years.
Oh, okay.
This is through a few things, but it's particularly through a new medical and life sciences research lab that I've just helped start, and I'm now the chair of, called WAMRI, the Wicklow AI and Medical Research Institute, and it's at USF, University of San Francisco, and we basically invite medical researchers and life science folks to partner with us, and we'll help with the deep learning stuff, and they'll help with the domain specific stuff. Yeah, so through that collaboration, one of the things we've been working on is helping Salk Institute to get better results from their microscopy, because they're world leaders in this area, and it turns out that if you can get really high resolution microscopy, then you can literally learn. They have been publishing papers showing breakthrough understanding of how proteins fold and how that actually impacts cells and stuff like that. So so initially we were kind of looking at GANs and getting pretty good results, and particularly one of our previous students, Jason Antich, has created this awesome thing called de-oldify, which takes old black and white low resolution photos and turns them into beautiful color pictures. And so he's been helping us with some of this work of getting GANs to work reliably, because he does better practical work with GANs than anybody else I've seen.
And how would GANs play into this Salk Institute use case?
Well, it's you've got these microscopy results. You want to get the highest resolution output you can from whatever input comes out of your microscope. And so there's actually been some very high impact work in microscopy recently on using SuperRes for that purpose. But it turns out, not surprisingly, that research was not at all using kind of modern deep learning methods. And so it's clear we can do a lot better. But then, as I say, then it turns out I've kind of realized that there are certain loss functions we can use which avoid the need for GANs entirely. So I'm now wondering if I wasted all that time. But I'm very interested in generative models, you know, and to see the stuff that's happening in the world of life sciences, you know, through better using whatever signal they can get from their microscopes. It's really exciting, you know.
Yeah.
And you really need domain specialists and deep learning specialists working very closely together, because like there's all these cool things that they can do that I wouldn't have otherwise known about, and vice versa. So for example, they can like, while they're kind of taking the picture, they can like change the wavelength of light they're using, they can change the focal length they're using, they can change the angle that they're using, and they can kind of end up with this like long exposure, almost like a video. And so we can then get this whole extra dimension, and there's this kind of sub-pixel resolution embedded in that. It's, I mean, this is exactly what we hoped for, honestly, when we started Fast.ai, is that kind of domain experts would be able to use deep learning to do a better job of whatever it is they're doing. So it's nice to see that really happening.
Have you seen any applications of GANs outside of the image domain? I kind of wonder conceptually you should be able to apply this to text and maybe do some of the things that people are using RNNs and LSTMs to do.
Yeah, well, like I say, I feel like people are putting adversarial in everything, and I'm not convinced it's helpful. I think often it's a bit of a lazy shortcut, you know, of like actually thinking about what your loss function should be. Yeah, I mean, you mentioned text. It's a good question. I think the more general question in text is what kind of like augmentation and stuff can we do in text to be able to use less data and get better results. And I've kind of seen some sign of trying to use adversarial approaches there, which I don't think is necessary. Like there was a recent paper in the last few weeks, which was basically, I don't know if you're familiar with the cutout paper. So,
No.
Okay, so you've got dropout, which I think everybody knows, which is like removing activations at random. And then the cutout paper in Vision specifically removed whole contiguous sections of an image, so kind of cut squares out of it and use that as regularization. And then there's been a more recent paper in the last couple of weeks, which has kind of basically done cutout at every layer of a neural net. So it's basically dropout, but instead of removing activations at random, you remove activations that are next to each other. Stuff like that almost certainly will work equally well in text, and don't require any of this kind of adversarial stuff. So yeah, so I think my view is probably GANs are a little overhyped and adversarial attacks are a little overhyped, but it's certainly a great way to get published at NeurIPS.
And you feel the same way about RL. Have you also experimented with RL?
Well, kind of. I spent 10 years kind of studying optimization more generally, and I never felt like these standard differentiation-based approaches, when you've got this kind of long-term credit assignment issue, necessarily make a lot of sense. And I still feel like there's a lot of the optimization literature that's being ignored by the RL community. You've seen a little bit of like evolutionary algorithms get touched on here and there. Like I think Uber did some work there. But when I think back to like all the stuff that was going on in the early 90s, people are just starting to rediscover some of it. So for example, in the early 90s, combining evolutionary algorithms together with kind of gradient-based methods was really common. And I just saw a paper literally reinventing it like 2 weeks ago. The problem RL is trying to solve is great, which is like, hey, let's not just try to predict things, but let's actually try to figure out what action to take.
Right.
But I feel like currently the RL community is not quite treating it as differently enough as it should be. It's, you know, when I spent a long time on optimization, it became clear over time that it's a good idea to kind of recognize the differences between prediction tasks and more general optimization tasks.
This is interesting because I had a chance to chat with Sergey Levine last night, and we were talking about just generally what he's found interesting over the past year in RL in particular. This was informal. But one of the things that he mentioned was a paper, TD3 paper, Twin Delayed Deterministic Policy Gradient, which sounded like just the kind of hack that you would love. Like it's a tweak to the way they do the policy that, like, he didn't even go into the details because it was such a nit, but it gave him, 2x better training times. So if, Fast.ai was doing RL, it would be just the kind of thing that you'd bake into the library.
Yeah, but I mean, we only work on stuff which clearly works in practice for the kinds of problems that most people have. Levine's one of the very few people who's using RL in very appropriate and useful ways at the moment. So for stuff involving robotics, there's a lot more you can do with RL, because anytime you've got some physical system that you can actually model with physics pretty accurately, you can kind of pull it apart and add appropriate constraints and add appropriate kind of auxiliary losses, and there's a lot more that you can do. So I think, the stuff he's doing is interesting and useful. But a lot of people are using RL for stuff. I don't know. I just went to the start of the health workshop here at NeurIPS, and there's all these people tackling kind of various medical problems using RL, which just seem like, I don't know, slightly ridiculous in my opinion.
Interesting. So there's been, we were chatting before we got started, and you mentioned some of the work that's been happening to try to better understand the way some of the tweaks we've been doing, like batch norm and other things, are working. Can you elaborate on some of that work?
I would love to. I mean, I feel like that's something where there's been some great progress this year, and particularly in the last couple of months. There's a fantastic poster here at NeurIPS that's been in archive for a while called Visualizing the Loss Landscape of Neural Nets. And what they basically showed is it's something I've been talking about for ages, but never actually did anything about it, which is this idea that you can have kind of this idea of sharp kind of parts of the loss surface, where if you're in a sharp part of the loss surface, then the idea is it probably won't generalize very well, because if you change anything a little bit, now you're not in that kind of nice low area anymore. And there's this kind of overreaction to what I thought was a kind of a obvious and kind of mathematical issue, which is how you can reparameterize the weights to make anything arbitrarily sharp, which to me, if anytime you can reparameterize something, why don't you just normalize out that reparameterization? So this visualizing the loss landscape actually did that. So they actually did the normalization, and then they did this, they built some beautiful software and some beautiful visualizations to show what happens. And they found some really interesting things. One of the most interesting was they found that when you look at the actual trajectory as you train neural net, for example, if you take the PCA space of the weights, there's basically only 2 dimensions. You can basically plot the entire, well, they said 40 to 90% of the variation in the direction of the gradient updates lies in just 2 PCA directions.
Independent of the dimensionality of your...
Well, this was on ImageNet.
Oh, okay.
So, I mean, this is obviously super high dimensional, so, over 100 million weights. And so, one of the nice things that means is you can kind of plot pretty close to exactly what's going on, which they did. And you can also plot the loss landscape that's being navigated. And so one thing they found was as soon as you add skip connections, so ResNets versus the exact same net without the identity shortcuts, ResNets basically make the whole surface incredibly smooth. And dense nets make it even smoother, by the way. So when you see their pictures, it just immediately makes you realize, okay, this is why we've all been loving ResNets so much. And so you can kind of see similar stuff with normalization. So one of the really interesting papers to come out in the last couple of months, so there's been 2 papers coming out very similar times, which both basically said, hey, you know how batch norm was meant to help with covariate shift? Well, it turns out it doesn't help with covariate shift, and it's got nothing to do with covariate shift. And actually what it does is it makes the loss surface smoother, which actually, if you think about it, makes perfect sense. You know, if your current activations are scaled really poorly, then if you don't have batch norm, the only way to fix that is to modify all of your weights on that layer. Or else if you do have batch norm, you only have to modify the batch norm weights to fix the scaling. So it just makes the loss surface a lot smoother. So then there's been other very nice kind of follow-ups to that. Well, not exactly follow-ups, coming out at similar times to that, saying, hey, here are some different ways of doing normalization which don't focus on the covariate shift, but focus on the scaling. So spectral norm and weight norm in particular, which are now both built into PITorch. And when you create a conv layer in Fast.ai, you can literally pick from an enum of what norm type you want. And yeah, they help a lot actually with, again, stabilizing training. So yeah, all these kind of insights into what's going on inside the neural network is helping lead to better ways to train the neural networks, which means less hyperparameters, less, more resilient, higher learning rates. It's all making life easier in practice, which is great.
So last year, the big controversy, at least one of them, was Ali Rahimi's kind of call for greater rigor. Do you feel like a lot of this work is a response to that, or?
No, I never quite figured out what Ali meant, and even though I had quite a few private chats with him, I never quite figured out what he meant. I tried to dig into it. I think, yeah. So I since I don't quite know what he was saying and haven't figured it out, I can't quite. I mean, he's a great speaker, and so a lot of people were like, "I really liked that talk." But when I asked them, like, what exactly did he mean by rigor, and exactly what are you going to do about it, no one had a good answer to that question. So, for me, as a kind of an experimentalist, I think rigor is about ablation studies. So if you look at the ULM fit paper that Sebastian and I did, we spent a lot of time doing ablation studies. So we said, like, what if you did this with more data versus less data? What if you removed this training thing from this training thing from this training thing? What if you tried this data set versus that data set? And so we just had lots of tables and pictures saying, here's the things showing you which bits help and how much they help and what they help with. So to me, that's, when people don't have that, I don't find their papers terribly useful because I don't know what's actually helping, and often the things they thought were helping weren't helping. Even worse for me is when people don't use a strong baseline. So they'll have some really crappy model and they'll say, like, oh, look, our technique X improves that crappy model. But when you look at it, it's, their technique X is just a crappy way of doing what the normal baselines would have done anyway. So I think, like, to me, in terms of experimental work, strong baselines and good ablation studies is what it's about. But, for the NeurIPS crowd, rigor often means Greek letters. They want to see, like, convexity proofs and error-bound proofs and all this stuff, which I've just never seen useful. Like, the only thing I've seen those kind of proofs do is to totally mislead people. So, like, we had what I call the SVM.
That's pretty strong.
Yeah, it's true. We had what I call the SVM winter for, like, 15, 20 years, which is basically, Vapnik did this really, to some people, compelling paper. It's just kind of like, hey, all you need is SVMs. Here's the mathematical proof. And when you actually look at it, it's the things that people took out of that are rubbish. Like, it's the difference between, like, in theory, here's what ought to work versus in practice, here's what actually works. So it's nice. This year, Leon Bateau's, I can't remember the co-author, but Leon Bateau's work won a Test of Time Award, his 2007 paper, which basically I mean, it's ridiculous that it was necessary for this paper to even happen, but he basically said, look, all you people who are spending all this time on like fancy optimizers for SVMs, actually SGD works better. And and then here's all the Greek symbols you need. You know, like here's all the proof and math and whatever else. So like there's already plenty of experimental evidence to say like it works better, which most of the community ignored. And so it really took somebody to come along and like say it in their own words and to like prove it. So to me, I'm kind of like, I don't know, like similar thing with like going back further, Minsky, right? Minsky like proving that neural nets are a waste of time because they can't like solve the XOR problem. And so the thing is, all these mathematical proofs, they're always of oversimplified versions of the problems we're actually trying to solve, because the problems we're actually trying to solve are not amenable to that kind of analytic approach. So, you know, took 20 years really for somebody to come along and say, well, we're not just using one layer, you know, we can actually have a hidden layer. And if you have a hidden layer, then we can solve any arbitrary problem to arbitrarily close, given enough parameters. So again, like these kind of AI winters we had were really kicked off by people taking theoretical results far further than they should ever have been taken and ignoring all of the empirical evidence of like, I don't know, like guys like Jan LeCun, who's like saying like, hey, I've actually written this thing, Linnet 5, that actually reads numbers, you know, it works. It uses this thing called a convolutional neural network. And, you know, people like that just weren't getting published because, you know, because the theory had already proven that we should be using these other approaches. So, yeah, I think that's a concern I have about our field in general. It also is a real problem for diversity and inclusion because there's lots more people in the world who know how to code or, you know how to do some engineering, but won't know how to prove error bounds on something or whatever. And also like we'll be much more focused on like, hey, I want to actually solve this problem in medicine or in, you know, disaster resilience or whatever. And so they'll want to be publishing papers saying, here's thing A that works for thing B. And the current focus in our field is very unfriendly to that kind of stuff.
Interesting. Yeah. I'm curious, having launched the new Fast.ai course this year, the deep learning course, any specific 2018 learnings about deep learning education or what's required, what's needed to kind of broaden the fold of folks that can do deep learning?
I think I've been surprised by how far people have gone on the back of the Fast.ai course. Like a lot of presenters at NeurIPS have come up to me and said they got into deep learning through Fast.ai. And if you had asked me 3 years ago if our students are going to go on to be researchers presenting at NeurIPS, I would have been like, that sounds unlikely. I feel like we're just trying to get people to be reasonable practitioners. So I think that's been a pleasant surprise. I've also been a bit surprised at how quickly the software has taken off. Like for me, that's kind of my focus now, is like I would love the software to be as standalone as possible and not really require people to do the course, because there's a lot of investment in time to do the course. And yeah, I'm increasingly running into particularly researchers now who have come from backgrounds in TensorFlow or pure PITorch or Chainer or whatever, and kind of saying like, oh, I started using the software and my research is going faster than it was before. So that's been nice. But I think overall, we've kept on finding the same things we've found in previous years. It's just accelerating. Like I went to the Black and AI dinner last night and the Black and AI workshop, which I saw you there as well. It was just so great how many people came up to me and said like, hey, I'm from the Ivory Coast, or I'm from Tanzania or whatever, and I had no way to learn deep learning until your course came along, and now I've done it, and now I'm here at NeurIPS presenting at this workshop. And they're always like kind of inspiring stories, because often they were telling me last night about the steps they had to go through to get a visa, often having to go to other countries and contacting the consul general to, because they're forging paths no one's ever forged before.
Right.
And now they're finding communities. So like, it's so cool the way, like 3 years ago when we did our first course, we had one student from Lagos, and he was like asking on the forum, like, hey, anybody else from Lagos here? Anybody else from Africa here? Can we have a community? No, nothing, and now Lagos is our second biggest Fast.ai community outside of the US. So Bangalore is still the biggest by far, but Lagos is huge. So like, it's been really cool to see how just a little bit of, and I know it's certainly not all thanks to Fast.ai. There's lots of people doing great work here, but I know like plenty of the people involved have got there thanks to Fast.ai. So for example, one of the people presenting at the Black and AI dinner last night, Judy Chachoya, she's a radiologist who got into deep learning through Fast.ai, and now she's like a incredibly kick-ass leader, both in the radiology world and in the deep learning world, in the Black and AI world. So I feel like there's now enough momentum going on that these underrepresented groups are not going to be underrepresented for too much longer.
Yeah, I thought I forget his full name, but one of the presentations was Kareem Karim. There was an interesting slide where one of the speakers from Tunisia kind of asserted that AI is both this incredible, both a existential threat for Africa in some ways and an awesome opportunity, and kind of, for him, it was a rallying cry to, get more people engaged in the process. I thought that was really interesting.
Yeah, I mean, that's kind of why Rachel and I started this. It's exactly why Rachel and I started this, is we both thought like, this has the potential to massively increase inequality. And that is exactly what will happen if there's just the status quo.
Right.
Because all the people, before we started Fast.ai, all the people pretty much studying and working in deep learning were, Western, white men, who very, very few of whom had any kind of domain expertise background. So they were using deep learning to solve kind of bullshit problems. So we thought, okay, if nothing changes, that's going to get worse and worse, because those people keep getting money thrown at them, and they keep hiring more of the same people and investing education in the same places. But at the same time, it's deep learning is not that hard, and it can be used to help so many areas with so many problems. So if we could get the skills out there, then maybe people who otherwise would not be able to will be able to like make a big impact. So I mean, Judy's a good example. I think she's from Kenya, and I'm sure she would have been a great radiologist regardless, right? But I feel like now, we have somebody in the kind of senior thought leader community amongst radiologists who is Black and who is a woman and who is, both bringing AI to radiology and radiology to AI. It's exactly the kind of perspective which, I think can create opportunities where they didn't exist before.
Let's talk a little bit about the tools landscape. Obviously, one of the big developments in 2018 was the launch of the 1.0 versions of both the Fast.ai library and PITorch. Is it too early to talk about kind of momentum from the PITorch launch? Or are you
it's not too early,
things?
because one of the really interesting things has been to see TensorFlow's reaction, which is they've really got off their ass and are doing good stuff. They made some tough choices like getting rid of tf.contrib, making TFO a much more community-driven exercise. I think they realized that, the direction, you talk to almost any Google TensorFlow engineer, off the record at least, and they'll tell you they all hate that code base. It's full of technical debt and it's just not well put together. And it's not focused on the kind of the developer experience. It's really focused on using as many TPUs as possible. So TF2 is looking like a huge step forward in terms of the developer experience and, just kind of a piece of software that people will enjoy using rather than use because they have to. So, and I really think that's been, I know it's been very heavily a reaction to PITorch, which is not to say PITorch invented this approach. Chainer certainly did it before PITorch, and I don't quite know the history before that, but I think, realizing that the tools need to be written for developers is just a really important insight. So I think I think the impact on the TensorFlow Gorilla has been important and interesting. But then, people just using PITorch, particularly in the research community, you're definitely seeing things, more innovation as a result. You're seeing faster innovation. And then, the impact of Fast.ai is probably a little early to really know, but we're seeing that for a whole nother level for the, quite a few researchers who have picked up Fast.ai. And, Fast.ai kind of has two different user groups in mind. There's the, very much the research user group. So that's all about the kind of lower level of abstractions where, so for example, with our GANs, we've made it so you can easily do research around, like, if you want some dynamic approach to switching between training the critic and the generator, you can just plug in your own GAN switcher class. Or if you want to pre-train a different kind of critic, you can plug in a different pre-trained critic class, whatever. And then, of course, there's the user group of people who just want to get something working at their company. So, for example, one person who came up to me at NeurIPS last night said, my company has 3 million documents. It's a pretty big international company, and we've been using Fast.ai and ULM Fit to basically tag all 3 million documents. And they have a full-time taxonomist who sits there and classifies documents, and then that gets fed off to ULM Fit through Fast.ai, and then they look at the results and fine-tune the model. And, so they're not doing research level customization or whatever. They're just getting stuff done. So I think both of those groups are, I think previously they would have been using Keras if you wanted to do something like that, but Keras just doesn't really give you easy support of things like NLP and things like that. So I think that, maybe that's one of the main impacts of Fast.ai in that area is easy. Deep learning isn't just in computer vision anymore. It's also NLP and tabular and collaborative filtering.
Any other interesting things on the tool side that have caught your eye?
There's plenty of stuff going on. I wish I had more time to dig into them than I did. I mean, in the PITorch community, obviously one big thing in PITorch version 1 release, which just came out yesterday, is the just-in-time compiler. So you can add a JIT decorator to your code and get, fused, fast inference version of it. So there's quite a bit of that stuff going on. There's another much less known library for PITorch, which is the Gaussian processes library. And to me, it's not so much interesting because of the Gaussian processes, but it'd be interesting because they have something called a lazy tensor, which kind of takes the JIT to a whole nother level, which is you can, as you basically say, these are all the mathematical operations I want to do on my tensor, it's just storing the computation graph. It's not doing the actual calculation at all until later on when you just say, compute, and then it compiles a kind of a fused version, much faster, handles kind of stuff like sparsity and stuff much better. And they also have some kind of nice linear algebra identities, which they use to, just use arithmetically much better choices when they know that, you had these different shaped matrices and you did these particular operations to them, and this linear algebra identity, so therefore we can replace that set of operations with this single faster one.
At least with the lazy tensor, is this an example of kind of PITorch moving towards TensorFlow while TensorFlow is moving towards PITorch?
I think so. I think so. Yeah, exactly. So the kind of the JIT in PITorch is starting to feel a bit like XLA, I guess, in TensorFlow, but with less technical debt. Yeah, and the kind of the lazy tensor stuff is starting to look a bit like the kind of static graph approach, but without all the horrible boilerplate that you need in TensorFlow. So, I mean, where I'm really excited though is what TNG Chen is doing with TVM. Like, hopefully that stuff with TVM where they're...
Can you elaborate on that? What's TVM?
TVM is something that's basically at a lower level, which is that you take it's basically a compiler for tensor expressions that will create an optimized version of your tensor expression. And because at the moment, one of the things I hate is I hate it when I say to a student, like, okay, let's dig into this code, which calls this, which calls this, which calls this, and let's understand all the stuff that's going on. And they get to a point where it's like, oh, and this calls NVIDIA's cuDNN library. So at that point, okay, after that, it's magic. So one of the cool things TVM does is it kind of lets you see, it doesn't suddenly stop at cuDNN. It's now, here's the TVM code,
Okay.
And then TVM ends up, believe it or not, faster than cuDNN, even though TVM is automatically creating that optimized CUDA kernel.
So is it a replacement, or is it compiling down to CUDA or something?
I mean, it still has to compile down to, not necessarily CUDA, but maybe PTX. So it's still, so it's not, but it's not just for NVIDIA. It can also target, ARM or, various mobile devices or CPU. So I'm kind of like excited about this because I think it might mean that, particularly for stuff like Swift for TensorFlow, which is a project I'm really excited about, hopefully we can see things where we can write everything we're doing in our kind of host language. And
I was going to ask, are you excited about that because you're excited about Swift the language, or because you want to see deep learning accessible via all the languages?
There's a number of reasons I'm excited about it. One is that I hate Python, so it'd be great to get rid of it. It's just incredibly frustrating to have to write in a language which has so many kludgy things, like the global interpreter lock, and just so incredibly slow every time you actually do something in Python. And so it's very, very frustrating to work with. It's fine if you're doing a web app or something, but for numerical programming, you spend all of your time trying to figure out how to have everything not being done in Python. You're basically always calling to C or CUDA or whatever libraries. Partly it's because Chris Latner, everything he touches is awesome. So it's just nice when somebody like that comes into your field, and I just can't, I just love seeing what he's doing. Partly because Swift is just, it's a good language. It's, there's a few good languages in the world, like I think F# and Julia and Swift are all examples of just good languages. But the thing about Swift and Julia and F# is they can all, you can write fast code in them. And so Chris's approach with the Swift for TensorFlow team is that you'll be able to write all of your CUDA kernels and stuff in Swift, and so, and because like he's the LLVM guy, he's got the compiler chops to make sure that those Swift kernels are not going to be any slower than the C kernels will be. So also from a teaching point of view, it'll be really nice to be able to show people every layer. And from a research point of view, it'll be really nice because we'll be able to swap out this LSTM cell with our own LSTM cell and not have to, worry about, switching into C++ and compiling an extension and then dealing with a whole different debugging framework and all that.
How far along is that?
Not terribly far along.
Okay.
It's not. Some of our students have tried to kind of play with it, and it's not really usable yet. But I'm sure it'll get there.
Okay.
And similar stuff going on in Julia, by the way. Julia also has some really exciting stuff going on around writing kernels in Julia and all that.
Okay. So maybe switching gears to 2019 and things you're excited about, opportunities. What are you looking forward to? Or what do you think is going to happen I don't know if you're one for kind of dusting off a crystal ball, but...
No, I don't even know what I'm going to do, let alone other people. I mean, we'll just keep doing what we're doing, I guess. I'm going to be doing a deep dive into speech recognition kind of next year. We're going to write a book about Fast.ai and PITorch, kind of the book version of the course, I guess, early in the year with Sylvain Cougar, who has been helping us with pretty much everything this year. I hopefully will keep lowering the bar around. Hopefully we'll start getting to the point sometime soon. I don't know if it'll be in the next year where we can do useful stuff without any code. That's really the main bar that I want to get to, is doing useful stuff without any code.
What does that mean for you?
So there's this startup I'm involved in called Platform.ai, where we're trying to do exactly this for one particular subdomain, which is image classification. So you can don't even need labels. You can import some photos, and we try and provide a kind of intuitive representation of what the model is learning to help a domain expert interact with it in an entirely visual way. So for me, it's all about like people using stuff like that to solve scientific problems or to optimize their logistics or whatever it is they're trying to do, it's all about recognizing that machine learning is computers learning from examples. And so that should be all about getting rid of code. You shouldn't need for loops and conditionals and stuff. You should just be able to say, here are my examples. And the computer said, here's what I'm learning. And then you should say, well, here is some feedback about which ones are right and wrong. So that's where we want to get to. So we've already got this startup doing that for computer vision, and I hope to do similar things in speech and NLP as well. As long as we rely on people knowing how to code, we're missing out on something like 99.9% of the global population.
Right. So maybe, not kind of being so strict about 2019, just, looking ahead to the near future, what, where do you think the opportunities for us lie, or are there specific ideas, or even some of the ideas that we've talked about in terms of, better understanding of the way some of the training techniques are working, or...
So the big opportunity right now is NLP. So, this year we and others showed that transfer for learning for NLP works. Specifically, it works without requiring any manual labeling, other than for your target task, and even then doesn't require much labels. We're going to see, I'm pretty sure, similar things being shown for generative models for text. So unfortunately, that means one of the big opportunities will be that spammers and trolls and people interested in disinformation will be able to use this technology to cause much more mayhem than they've been able to cause before. So I would say that's probably going to happen in the next 12 months. So I would not be surprised to see massive scale bots of generative text, which are both appropriate enough to the thing it's responding to seem reasonable, and kind of reasonably believable stylistically, that large numbers of people will be fooled by them large amounts of the time, and they will not be easily automatically blocked or even analyzed to know the scope of them the way that things are now. So
do you think the technology to fight that is harder than the technology to create it, or is it just the will to...
No, it's much harder to fight.
Okay.
I feel very confident that if I had the reason or motivation to build such a bot now, I feel very confident I could create one at scale which would, be devastating to any social media platform. And I think lots of people, I mean, not lots, but, anybody involved in the modern NLP kind of transfer learning stuff could. I would have if somebody said to me like, hey, Jeremy, Sebastian Ruder's just become an evil genius and has written a Twitter bot to spread Russian disinformation. Can you go and help block it? I'd be like, no, probably not. I don't know. That sounds really, really, really hard. And that's often been the problem in these kind of areas, is it's normally easier to create mayhem than to block it. And also when you're trying to block it, you're always kind of being reactive, particularly where we're not using more heuristic approaches to do the generative modeling, but using kind of smarter approaches. So yeah, I think that's going to be a really big problem. And one of the challenges is that the best way to fight that would be to write your own generative text bots and use them to fight the disinformation. But the kinds of people that would want to fix the problem would be much less likely to be the kinds of people who would be prepared to launch their own generative text box. So I think that'll be difficult. But then I think, there's a lot of opportunities to, in industry for companies to be able to use text as a valuable resource. I think it can certainly happen in medicine as well. Like one of the challenges in radiology is that the labels are all buried in radiology reports.
Right.
And when you look at stuff like the data sets that the NIH have provided for medical imaging, the labels they've created have been using classic rules-based NLP approaches, and they're just terrible. So having that labeling done with these kind of modern transfer learning approaches will be awesome. So yeah, I think that's hopefully going to be one of the big, at least the positive side of it will be one of the big things in 2019. I think we're going to see these different approaches to normalization probably start to take over from batch norm. I mean, it's kind of unfortunate that we don't have a real ImageNet competition anymore, because like ImageNet, has plenty of flaws, and I'm not saying we need ImageNet back, but the fact that there was our competition that quite a few of the more serious researchers decided to invest significant time in meant that each year you would see, this year we've got 3x3 convs. This year we've got ResNets. This year we've got, Andrew Howard's data augmentation methods. Like they were like, it made people who would otherwise be focusing on mathematically pure whatevers, like actually focus on solving a problem properly. So I do worry that, and also those solutions got published not just as papers, but as, pre-trained models that we can download. So I do worry a bit that we might continue to use pre-trained ImageNet models with older architectures and older normalization approaches and stuff, just because we don't quite have an ImageNet competition anymore. So I don't know what the fix to that is. I mean, there is like TF Hub, and now there's a Torch Hub, which actually provide pre-trained models. But people need to start realizing, I think, that the ImageNet models are increasingly out of date. I think. And then, skip connections are still interesting. The UNET paper is now the most highly cited MICI, Medical Imaging Conference paper of all time. ResNet obviously is still kind of all-powerful. So two really important skip connection stuff. So I think hopefully people will keep finding ways to better utilize skip connections. And those two things, skip connections and normalization, really help make models easier to train quickly and accurately.
I think the rate at which new data sets are coming online has been increasing. There have been a ton of these in like various domains in 2018. Do you think we see, or need for that matter, like a kind of a better ImageNet or a monster, kind of the image data set to end all image data sets? Or do you think the domain specific direction is better?
Yeah. So Google, to their credit, just yesterday, maybe it's this morning, released a much more diverse version of open images. And that's really fantastic because previously the open images and ImageNet datasets were incredibly biased in terms of they basically all came from white Western countries. And so that made it very difficult to train models that could recognize Hindu weddings versus Christian weddings, for example. I think we have great photo object classification datasets, but we don't have great microscopy, histopathology datasets. We don't have great radiology datasets.
On the text side, NLP side?
On both, yeah. Particularly thinking of vision. On the text side, I mean, it's ridiculous. There are almost no publicly available labeled text data sets that normal people can use as they wish. Most of them are locked behind this thing called the Linguistic Data Consortium, which is part of UPenn. And I'm sure originally when it was created, it had every good plan to help research, whatever. But today it's basically this thing that is increasing the exclusivity of the field. So my students can't replicate results in papers because so many of the data sets in NLP are locked behind all kinds of licensing agreements. And one of the most popular ones, the Reuters corpus, you have to download, print, sign with your organizational affiliation a form and send it to the government for approval. And you can't have 100,000 Fast.ai students doing that. So I can't use those data sets because they just aren't they were created in a time when people just didn't occur to them that maybe there's more than just this little research community of people who go to my little workshop, but there's actually there's a whole world of people out there who are wanting to do work.
Right.
So that's a huge problem. So I think, I think something else I would really like to see is in areas like medical imaging where data sharing is difficult, I want to see more model sharing. So there's lots of pre-trained ImageNet models, more than we need. So where's all the pre-trained histopathology models and the pre-trained CT models and the pre-trained MRI models? Those are actually much more useful because, if Stanford releases their pre-trained prostate MRI model and then Boston picks it up and fine-tunes it a bit and publishes those weights, and then Harvard picks it up and fine-tunes that a bit and then publishes those weights, and then Stanford can come back and fine-tune that back in the circle and end up with something better than they started with. It actually has been shown that you end up with just as good a model as you would have if you actually shared the data, but all you actually have to do is share weights. So I would love to see people releasing pre-trained domain-specific networks.
So another thing we saw quite a bit of this year was proposals for data sheets for data sets, model cards, different representations of the idea that we need to document the biases and lineage in some cases of data sets and models. Do you see that stuff taking off?
I don't see it taking off, no. I mean, I think it's really cool the work that Timnit Gebru and all those folks did with the data sheets for data sets work, and some really interesting examples of other industries where that's happened. So I've done some work with electronics, and certainly I'm used to, as they describe in the paper, that every electronics component comes with a data sheet in a fairly consistent format, and you rely on it. Having said that, we're still suffering in the deep learning world from people not publishing their data at all, or not publishing their code at all. So I also worry about, like, if we say, like, well, you can't publish your data set unless you create this data sheet, maybe there'll be even less people publishing their data. I do think that all the conferences need to say, if you have experiments, you need to publish the code and the data. Right? People claim that we have this great peer review system, but when you actually look at it, it doesn't really work. Like, reviewers don't recreate the papers, write the code to recreate the papers, ever. On the other hand, when people put stuff up on archive, there'll be many of our students all at the same time trying to replicate it. And if they can't, they'll get up on GitHub and post issues and say what's going on, which has happened just a couple of weeks ago. It turned out that a widely cited paper, our students went to replicate it and found they couldn't, and discovered that the researchers had accidentally used the test test set as part of their training data. You know, so, like, I don't at all agree with this idea that we have to keep this pure, exclusive peer review system. What we instead need is for people to publish their code and publish their data, and then get it out there so that the rest of us can try it out. And I think the academic community still doesn't realize how many of us do that replication. Like, every single algorithm that Fast.ai teaches or implements in our software, we always re-implement from scratch and test from scratch, for example. And we're definitely not the only ones. So I think, like, are lots of people going to start publishing data sheets for data sets? Let's first of all have them publish data sets at all. It would be great if they, and I guess it's up to the kind of conference and venues and journals and stuff to start saying, first, yes, you have to publish your code and data. And then maybe once that's happening, okay, you actually have to also publish a data sheet to go with it. We could at least encourage through the review process in the meantime to, like, if you've got a new data set, to kind of say, like, can you, reviewers could ask for information about how it was collected and, what the diversity of people involved in was and stuff like that.
It certainly does seem like a good bar in a time when you've got 4,000 submissions to NeurIPS and 1,000 papers being published to require that folks that are doing experimental work publish the code as well.
It does. Yeah.
Well, Jeremy, it's been so great to chat with you once again. Great to see you here, and thanks for taking the time.
Thank you, Sam.
All right, everyone, that's our show for today. For more information on Jeremy or any of the topics covered in this episode, visit TWiMLAI.com/talk/214. You can also follow along with our AI Rewind 2018 series at TWiMLAI.com/rewind18. As always, thanks so much for listening, and catch you next time. Happy holidays.